And the first thing we're going to talk about is something called polar coordinates. If you have ever been to New York City, or specifically to Manhattan, then you know that the streets there and the avenues are all laid out in a grid. Okay, the avenues go north and south like this, and the streets go east and west like this. And if I want to give you directions on how to get from here to here, I'll tell you to go up 2 blocks this way, and then 3 blocks, turn left and go 3 blocks that way. That's how I would give you directions. That's just how it's laid out. That's how you wind up thinking. That's not the only way to give directions. Another equally good way to give directions is something that you see when you look at a roundabout. When you go driving and there's a circle in the road, you could be coming at it this way, right? And then you start going around, and then there's an exit here, and there's an exit over here, and there's an exit over here, and maybe another one here, and maybe another one here, okay? And I might tell you, if I'm giving you directions to somewhere, I might say, go around 2 exits, or maybe go 1/3 of the way around the circle and then take that road that way. Or if you're continuing along the same path, I would say, take the roundabout, go, and then continue in the same direction. Go halfway around the circle and then keep going in the same direction. And that's just a different way to look at things. It's a different way to give directions. And it turns out there is something else in math specifically, and that is looking at the same plane we were looking at before. Up until now, we've always looked at it in what we call rectangular coordinates, or sometimes Cartesian coordinates, after Rene Descartes, who's the guy who came up with the idea of taking 2 number lines and making them perpendicular to each other, and then giving the entire plane identities by saying, this point would be, or some point over here would be 3 to the right and 4 up. This is different. This starts here, the same way we do when we're creating angles, and we give you 2 different sets of, 2 different coordinates. One is we say, okay, rotate around the circle 2 pi over 3, and then go out 4 spaces. Okay, so I think that's 4, 1, 2, 3, 4, right? So you go there and you go 1, 2, 3, 4. That now has a different set of coordinates than what you would normally give. It's the same point as it always was, but that point would now be referred to as 4, 2 pi over 3. Okay, that would be this point right here. And that's a new way of thinking about things. It's the same point as it was on the other graph, on the other grid. It's the same point on the plane, but we've given directions on how to get there in a different way. In order to think about this, in order to think, obviously, one of the things you're going to want to be able to do is switch back and forth from rectangular coordinates to the polar coordinates. And how are we going to do that? Well, one of the things to remember, actually 2 things to remember. One has to do with the definition of cosine. If you remember, cosine of theta is equal to x over r. Okay, and sine of theta is equal to y over r. And tangent of theta is the slope, and that's equal to y over x. Okay, so that's one set of things to remember. The other set of things to remember is that r is equal to the square root of x squared plus y squared. Okay. Those are the things from trigonometry from last semester that you should remember. And before, the way we used these was to say, okay, if I gave you a point, right? Last semester I would give you a point, and let's say I gave you -3, +4. And I said to you, well, find out what you can about this angle here. Find out the sine, find out the cosine, find out the measurement of the angle. And you were able to do that by using this point. Okay, let me switch from this for a moment and see if I can copy this. No. So let's go back for a minute to this and say, well, how did we do this before? We would draw a coordinate plane, right? A Cartesian coordinate plane, and then use, right, we would give a point out here, and let's call it, let's call this, like I said before, let's call it -3, =4. And then we would say, well, what do we know about this angle? And the thing is, we know that -3 is this way, and +4 is this way. So we know the length of this, and we know the length of this. We know this is a right angle. So we could get this distance here by using the Pythagorean theorem. Right? We take x squared plus y squared, take the square root of it, and this right here would be 5. Right? And we called it r because we said it was the radius of a circle. We said this would be equal to r. And then the other thing we did was we looked at this right here and said, the slope of this right here is rise over run. So the slope of this, which is also called the tangent, right? The tangent of theta is equal to the rise over the run, which in this case is 4 over -3. Then we were able to take the arctangent of 4 over -3, and that gave us some value of theta that we got by using the inverse function. Put the inverse function in our calculator, and that was plus pi n, because that was the definition of arctangent. And the reason for that is you had this angle here, but you also had this angle over here, because one thing we know about the slope of a line is that if the slope of the line this way is something, the slope of the line that continues on this way is going to be the same. It's going to have the same slope. So I think your calculator gives you negative something here. But we know that that means if you add 180 degrees to it, that would give you this angle here. And the only reason we know that it's this way instead of this way is we know where this point is. We know that this point is in the second quadrant, so it has to be this angle. That should sound familiar to you. The first period group was sort of hazy about it, so I promised I would go find the video for that and pop that back up in materials. But in the meantime, it's this particular exercise that prepares you for what we're doing now. Okay. So this right here, if I knew the XY coordinates, I would turn it into polar coordinates by finding out this angle using the arctangent of the slope of this, the y over x. And I would find the length here by using the Pythagorean theorem. Okay, and that would, using x and y, that would give me the polar coordinates. If I'm given the polar coordinates, on the other hand, then there are two things I need to do. Okay. But it turns out that this is even easier. Why? Because, can I get back in here? Yes, I can. Okay. So keep in mind that if cosine of theta is x divided by r, then that means I can multiply both sides by r, and x is equal to r times, oops, that's not right. There we go. R times the cosine of theta. And the sine of theta is equal to y over r. I can multiply both sides by r and get r sine of theta is equal to y. So if I already know the polar coordinates here of 4, 2 pi over 3, I can actually turn this into xy coordinates by saying, I'm going to say x is r cosine of theta. So it's 4 times the cosine of 2 pi over 3, comma, 4 times the sine of 2 pi over 3. Okay, and that's the same when I do the arithmetic, right? The cosine of this right here is 1/2. So this is going to be 4 times 1 over 2. Actually, the cosine here is negative 1/2. And the sine is square root of 3 over 2, positive square root of 3 over 2. Okay. And when I do that arithmetic, what do I get? I get negative 2, comma, 2 square root of 3. And that's all really pretty straightforward. All you're doing is plugging these things into here.
Wait, sorry, where did you get the negative 1/2 from? I miss it.
It is the cosine of this angle, 2 pi over 3. The cosine is the x distance this way, and the sine is the y value over here. Does that look familiar? And if we know that this is 2 pi over 3, then we know that this point up here, if this were the unit circle, would be negative 1/2 rather over 1. And this here would be square root of 3 over 2 because this is a special right triangle. That's what you would do. Just really basic. You would take r cosine theta and r sine theta, and that would be your x and y.
So the 4 coordinate, that's the polar coordinate, and then the other one's like on the regular coordinate plane. But they're
exactly. Exactly. And let's go back for a minute here. I'm going to go back and say, here's my coordinate grid, and I'm going to give you the point, what did we say, negative 2, comma, 2 square root of 3. Okay. And we're going to say that that point is here. And if I take this, right, to be an arrow going through that point, well, what would I do now to get the polar coordinates for that? Well, the first thing I would want to do is say that r, in this case, is equal to the square root of negative 2 squared plus 2 square root of 3 squared. I would do that arithmetic and say that this is the square root of 4 plus 4 times 3, which is the square root of 16, which is equal to 4. Okay, so I know that r is 4. And then I would go over here and say the arctangent of 2 square root of 3 over negative 2 is equal to the arctangent of negative square root of 3. Well, I guess we already know what that's equal to because the inverse tangent of negative square root of 3 is 2 pi over 3 plus pi n. Okay. If you put this into your calculator right here, this inverse tangent of negative pi over 3, what you'll actually get is minus pi over 3. And we know that that's plus pi n. Okay. But we also know that negative pi over 3 is down here. And so it's in the wrong quadrant. So we've got to come back over here. If you recall, this whole thing about arctangent, arcsine, arccosine, your calculator gives you a clue as to what you're looking for, but you have to actually think about, you know, which one of these is really giving us, is it really giving us? So in this particular case, it's got to be 2 pi over 3 over here, which means that we're using 1 for n. But that actually tells us the polar coordinates, because now the polar coordinates are 4, comma, 2 pi over 3, which is what we knew because we were working backwards from something we started with. Let's go back to this and talk for a minute about the fact that we get different answers. Right? We got different answers here for the same point. And there are an infinite number of ways that we can get there. one of those ways is to just go around 2 pi over 3 and be done. But if you'll recall, another way to do it is to go all the way around and then 2 pi over 3 more. So it would be 2 pi plus 2 pi over 3, which is 8 pi over 3. And then we can add another 2 pi and get there again, and another 2 pi. But wait, there's more. We could also go around this way. Negative 2 pi over 3, negative 3 pi over 3, which is negative pi, and then one more, which is negative 4 pi over 3. Basically, if I'm using negative 1 as my n, I would have 2 pi over 3 plus negative pi, and that would bring me all the way back around. So that I would write as 4 comma 2 pi over 3 plus pi n. And that would give me an infinite number of ways to write this point, which would include not only going around this way and then spinning around and around and around and still going out that way, but it would also include going around this way and then spinning around and around and around and around. But let's also keep in mind that one of the other things that I wound up with when we first did this, and we used the calculator, we wound up with something down here. We got this measurement right here, which was negative pi over 3. So there must be some way to write that as well. And there is. Oops. We have negative pi over 3. And then, of course, plus pi n. How is this going to work? Well, here, actually, this is 2 pi n. Okay, because what I'm doing here is I'm going this way, and I'm going all the way around, and then all the way around again, and then all the way around again, and that's what this is representing. But here, I went down to here, and then what happened? Well, instead of being down here 4, what I had to do was go backwards 4 to get there. So that's negative 4 instead of positive 4. Well, negative does not mean in polar coordinates what it means in the other. Right, here's the x-axis and everything negative is down here for y, and here's the y-axis and everything negative for x is to the left. Doesn't mean that at all in polar coordinates. What it means instead is I have you standing here, and what I'm going to do, right, and you're facing 0 because that's where you start, and I'm going to tell you to spin around an angle and then walk 4 spaces. So I would tell you spin 2 pi over 3 and walk forward 4 spaces. And with this 2 pi n thing, it means I might say to you, okay, spin completely around once and then go 2 pi over 3 and then walk 4 spaces forward. Okay, 1, 2, 3, 4. Well, actually, this is 5 spaces. If I really wanted to make you very, very dizzy, I would tell you spin around 8 times and then go 2 pi over 3, and then walk forward 4 spaces. But one other way to get you to this point would be to tell you spin around negative pi over 3 and then walk backwards 4 spaces, 1, 2, 3, 4. Or if I really wanted the ultimate cruelty, I would say, okay, spin around the other way 8 times, and then go one more negative pi over 3, and then walk backwards 4 spaces. No matter what I do there, right, I'm going to get you to the same point. Right? And this should be 2 pi n here. So here are 2 infinite sets of ways to give you directions to get to this point, which is sort of crazy. If you remember, for the xy plane, any given point on the plane has only one way of getting there rectangularly. And this is sort of important too. If I have a point on the plane, there is basically a function that will give you your xy coordinates. You say, well, wait a minute, what is the function? Well, a function is just a set of rules, right? And the function was count how many spaces left or right, and then count how many spaces up and down. Those were the rules. And if you followed those rules, there was only one possible answer you could get. For polar coordinates, it's not a function. What do you mean it's not a function? What I mean is, if I give you a point and ask you to give me the coordinates of the point in polar coordinates, there's not one answer. There's not one output for the input. The input here is to identify a point, right? Literally point to the point and say, okay, give me the polar coordinates. Well, you might say, go this way and walk forward, say, 4 spaces. Somebody else might say, go this way and walk forward 4 spaces. A third person might say, no, go this way and walk backwards 4 spaces. All of those would be valid directions to get to this point, but they're all different. How are you going to, how am I going to know which one to give you if you ask for it? How do I know what the right answer is? And it's pretty simple. If I don't give you any instructions at all, and I just say, give me a set of polar coordinates for this, you can give me any one and you'll be right. More often, what will happen is there will be some restrictions put on this. Give me all of the polar coordinates on this that have an R value that's positive. Then you would give me this. And if I say, give me all of the possible polar coordinates of this with a negative R value, then you would give me this. Or if I said, give me all of the possible coordinates of this point where the angle is somewhere between 0 and pi. There's only one point you would be able to give me because I've restricted where you can put your angles. And if I said, give me all the possible coordinates of this point where the angle is restricted to be from 0 to 2 pi, there'd be 2 ways to do it. There'd be one way would be to give me this angle and the positive R, and the other would be to go all the way around to here and give me the negative R.